Alright, so here we have the covariance matrix and its 5 eigenvalues 15, 5, 5, 0 and 0. Let me denote the covariance matrix by C. We can write CV equal to lambda V, where lambda is the eigenvalue corresponding to the eigenvector V, and let us assume that V is a unit vector. Okay. Now let me multiply on the left with V transpose. So I can write this nothing as lambda times V transpose V equal to lambda. Now V transpose CV is nothing but the variance along the direction V, right? And lambda is the eigenvalue corresponding to the eigenvector V. Now using this we can say that the variance captured along a particular direction is nothing but equal to the eigenvalue corresponding to the eigenvector, right? Now when in PCA we only look at directions which are eigenvectors, right? So now we can use this particular intuition to solve this question. So we can say that the top two principal components, okay, will capture the variance equal to the sum of the top two largest eigenvalues, right, which is nothing but 15 and 5. So we'll take the sum of them and we'll divide it by the total variance which can be captured, which is nothing but 15 plus 5 plus 5 plus 0 plus 0, which is nothing but 20 upon 25. Now that is equal to 4 by 5, which is nothing but 80%. Alright, so here we have the ridge loss. Let me denote it by L suffix R. So the ridge loss is nothing but equal to summation of W transpose xi minus yi whole square plus lambda times of norm of W square. Okay. Now it's norm of W square and the norm is the second norm, okay, L2 norm. Now I can rewrite this as, we can say that the loss or the regularized loss on dt, the training data set, is directly proportional to lambda, right? But from the graph we can say that on the training data set, the graph comes downwards as you increase the value of f lambda, the regularized loss decreases. So we can say that LR is inversely proportional to f of lambda. So using these two intuition, we can combine these two equations and say that f of lambda will be inversely proportional to lambda, right? Now on these options, only the first one is inversely proportional to lambda and the remaining three are all directly proportional to lambda, right? So the first is the correct option. Alright, so let's do a quick summary of bagging and boosting. So in bagging, we combine models which are called base models, which have low bias and high variance, right? And we combine them by using the method of bootstrap aggregation, okay? So bootstrap means simple random sampling with replacement, okay? And similarly in boosting, we combine the base models. So in boosting, the base models have high bias and low variance, okay? And we combine them by a method called additive combination, okay? So that is the method. So this is the primary difference between bagging and boosting, okay? Also in bagging we have random forests, right? And for boosting we have gradient boosted decision trees, okay? In bagging, one more thing we have to notice is that for random forests we use very deep decision trees, so the depth parameter will be high, and in boosting the decision trees are shallow, which is the depth is very low, okay? Now when you consider bootstrap aggregation, this is a technique which can be done parallelly, right? So for all the models you can do it, and similarly in boosting it has to be done sequentially, which means it cannot be done parallelly, okay? You have to do it one by one. And shallow decision trees are also called decision stumps, in fact the ones with decision length 1, right? So we can see that bagging corresponds to point 2 and 3 and boosting corresponds to 1 and 4. Alright, so in case of hard margin SVM, the prediction for a new data point is given as y is equal to signum of W transpose x. So signum is nothing but plus 1 if the value is positive and negative 1 if the value is negative. So in case of x1, W transpose x1 is positive because both W and x1 are in the same direction, right? So y1 will be equal to 1. Similarly for y2, signum of y transpose x2. So signum y transpose x2 is again negative because x2 and W are in the opposite direction, so it is equal to -1. So the first option is correct. Alright, so here we have the class conditional independence assumption in naive Bayes model. So we know that independence primarily means that the joint density or the joint probability density of corresponding to a set of random variables can be expressed as a product of marginal densities or product of the individual probability density function, right? So this is the whole idea of independence, and this can be extended to class conditional independence as well, right? So we know that, so instead of taking density functions, right, we will take the conditional density functions. So the first option is correct. So in this question, we have to first take the mean of both the set of data points. So for the data points which are marked as cross, the mean would be -2, -1. Similarly, for the data points which are marked as a square, it is 2, 1. Now to find the cluster boundary, join a line in between them. Okay, so we know that it will definitely pass through the origin, and origin is also the midpoint. Now you draw a line which is perpendicular to this particular line and passes through the origin, which is the midpoint, and this line will be the cluster boundary, and the equation of this line is nothing but 2x plus 2x1 plus x2 is equal to 0, right? That is the correct answer. Alright, so here we have a hard margin SVM which is trained on a linearly separable data set with a positive margin. The features are in R2. Let me draw a simple diagram and represent one class of data points by cross and the other ones by circles, right? So now here the linearly separable, so the line which separates them are given by black, which pass through the origin, and the red and the blue denotes the supporting hyperplanes, right? So the equation of this will be W transpose x equal to 1, and the equation of the blue line would be W transpose x equal to -1, right? So now we have to find the distance between these two supporting hyperplanes, right? So you have to find the perpendicular distance between this particular line given by W transpose x is equal to 1, which can be rewritten as W transpose x minus 1 is equal to 0. So this line from the origin, right, which is 0, 0. So what is that? That is nothing but W transpose times 0 vector minus 1 divided by the norm of W. How did I come to this conclusion? So you might remember from high school that the distance, or you can say the perpendicular distance of a line from a point, of a line say ax plus by plus c is equal to 0, from a point given by x0, y0, that is given by ax0 plus by0 plus c divided by under root of a square plus b square. So this under root of a square plus b square is nothing but the norm of W, right? So here W is nothing but the vector given by a and b, right? Okay. So now this can be written as -1 by norm of W. Again, we are considering the distance, so we have to take absolute value. So it's nothing but 1 by norm of W. So now the distance between the two supporting hyperplanes will be 2 times this distance, right? Which is nothing but 2 by norm of W, which is 2 by under root of 3 square plus 4 square, which is equal to 2 by 5. Alright, so in this question we have one parent class and 2 child classes. Okay, so in the parent class we've got 200 data points, out of which 50 are positive and the remaining 150 are negative. In the left child we have 50 positive points and 50 negative points, and in the right child we have 100 negative points. So that is all of them are negative, right? Now we have to find the information gain. We have to find E1, E2 and E0, which are the entropy corresponding to the children nodes and the parent node. Okay, so the information gain is nothing but the E0, the entropy of the parent node, minus the weighted average of E1 and E2, where the weights are nothing but the points, data points in each of the nodes, right? Okay, so let's compute E1. So E1 is nothing but minus of half log of half. So this is base 2, again minus half log base 2 half, right? So this half comes from 50 by 100. Okay, 50 of them are positive, the other 50 are negative. So the answer is equal to 1. So E1 is what? 1 is the entropy of the left data point, right? So similarly E2 can be computed as -1 log base 2 of 1, right? Because there is only a negative class, right? So 1 is actually 100 by 100. Okay, so you can also view this as saying that the purest node, okay, a pure node has entropy equal to 0. It means it has no entropy. Now we can compute E0 as -1 by 4 log 4 minus 3 by 4 log 4. So 1 by 4 comes from 50 by 200 and 3 by 4 comes from 150 by 200. Now this can be computed to be equal to 0.811, right? So the information gain is nothing but 0.311. Alright, so here we have a polynomial kernel of degree p. So the general form of a polynomial kernel of degree p is given by k of x comma y is equal to 1 plus x transpose y whole to the power p, right? So it says the kernel should always output a non-negative value, right? So this will always be a non-negative value when p is an even number, right? So in this case, the only first two options are even numbers and the second two are. Alright, so here we have 100 points for a binary classification problems, right? So let me quickly draw a rough diagram. I have x1 here and x2 here, okay? Now, there are two properties of the data points, okay? The first one is that x1, x2 is positive, which means either both of them are positive or both of them are negative, right? So the points are either in the first quadrant, right, or the second quadrant, right? And it's not equal to 0. That means none of the data points can lie on the axis, right? Okay. And the next one says that x1 times y is positive, which means if x1 is positive, right, if x1 is positive, then y is positive, and if x1 is negative, then y is negative, right? Which means, so y is positive means y is equal to plus 1, and y is negative means it is minus 1, right? So we can immediately say that these points in the first quadrant, they are all positive, okay? And the points on the third quadrant, they are all negative, okay? This is what we can immediately say. Now, one more thing, since none of the data points lie on any of the axes, right? So that means there is some positive difference, okay? Some positive difference between the origin and the data points, right? So that will correspond to the second option. Sorry, the first option, which says it is linearly separable with a positive margin. So this is correct, and it is linearly separable, definitely. That is something which we can observe from the with the rough diagram itself, right? So the first option is correct. The second option says the perceptron algorithm will terminate after a finite number of iterations when trained on this particular data set. So what is the condition for a perceptron algorithm to terminate? So if the data set D is linearly separable, right, and it has a positive margin, okay, positive margin, right? If this condition is satisfied, then we can say that the perceptron algorithm will converge, right? Otherwise, we cannot guarantee it may or may not converge. Okay? So the second option is also correct. The third option is definitely wrong, and the fourth option is also definitely wrong. Alright, so here we have a question on logistic regression, right? Again, it is trained for a binary classification problem, right? And it says the probability that a test point 1, 1 belongs to a class 1 is equal to some given value, right? So in logistic regression, we know that the probability, right, that a particular test point belongs to, some class, say 1, right? That is given by 1 plus e to the power minus of w transpose x, right? Where x is the data point, okay? So I think I should write, instead of x equal to 1, I should write y is equal to 1, right? The label is equal to 1, okay? So that is nothing but this particular quantity, right? So it's given that this is equal to 1 plus e to the power 2, right? That means, what does that mean? That means w transpose x is equal to negative 2, right? And what is x? X is 1, 1. So we can say, and w transpose can be written as, say, w1, w2, right, as a row vector because it is transpose, and then x, which is nothing but 1, 1, right? Now this is equal to minus 2, which means that w1 plus w2 is equal to minus 2. Now we have to check which of the following options actually satisfy this particular criteria, right? So you can see immediately that the first option is cool, the second option is cool, right? But the third option is not cool because the sum evaluates to 2, and the fourth option is also not cool. Okay. Alright, so here we have a linearly separable data set. See, linearly separable data set, that immediately implies that if you train a perceptron algorithm, right, it will converge, okay? And the question says the weight vector output by the perceptron algorithm on this data set can be expressed as a linear combination of the data points where the coefficients are integers, okay? This is important. Let's do it one. Let's look at what is the update which happens in perceptron algorithm, okay? So what happens in perceptron algorithm? We start with the zero vector, okay? W0, okay? This is nothing but the zero vector, okay? So let me denote it by this, okay? Zero vector. And given Wt, the update Wt plus 1 is nothing but Wt plus y times of x vector, right? Now, okay, so now what is y? Y is the actual label of the data point x bar or x vector, right? And this x vector is some data point where wt misclassifies x vector. Okay, so wt misclassifies x vector. So whenever you see that wt misclassifies a particular data point, you make this update. Okay, so that is the idea. And now we know that since y is the actual label, it is either +1 or -1, right? So now w1 is nothing but, right, w0, which is 0 0, right, plus y times of, say, x1. Okay, x1, and then this goes on, right? So wk can be written as, or let me write it here, w1 wk, it is nothing but w0 plus y times x1 vector, which is the data point. Let me denote it by y1. Okay, and then y2 times x2 vector, and so on up till yk times xk vector. Okay, now what happens? So w0 is 0, so nothing to do. Now this is equal to summation of yi xi vector, I running from 1 to k, right? So what does it mean? It means the weight vector output by the perceptron algorithm is a linear combination. See, it is a linear combination of the data points, right? And what are the coefficients? The coefficients are all integers. Okay, so all yi's are plus or minus 1, right? So they are all integers. So the first option is correct. Alright, so here we have a hard margin SVM problem. So in hard margin, what is the optimization problem? It looks like maximizing norm of w square divided by 2. So we have to maximize this with respect to a condition which says that w transpose xi into yi is bigger than or equal to 1 for every I, right? For every I means for every data point. Okay, so this is the primal problem. Now what is the dual of this? So the dual can be written as maximize with respect to alpha non-negative. So alpha is again a vector which is non-negative, and under this we have another minimization problem, which is minimize with respect to w, the objective function in the primal, plus summation of alpha I times 1 minus w transpose xi yi, right? Alpha i's are the new vectors which we have to find. So alpha belong to Rn, right? And the goal here is to find alpha, right? Okay, so these problems are the same. Okay, and also this term inside the maximization. So this term can be expressed as a function of alpha. Okay, or you can say it can be expressed in terms of alpha. Okay, how do we express it in terms of alpha? Now this is a minimization problem, so we take derivative with respect to w and set it equal to 0, right? So once we take derivative, we'll get w plus summation I running from 1 to n alpha I minus xi yi, right? Now that is set to be equal to 0. So we have w is equal to, or w star is equal to summation of I running from 1 to n alpha I xi yi, right? Or yi xi. Now xi, what are xi's, alpha i's and yi's here? So we can say that xi is nothing but a vector in Rd, right? And alpha is non-negative, and yi is either plus minus 1. Okay. So alpha yi is a scalar and xi is a vector. So this can be rewritten as x, y, alpha, right? Where what is x? X is nothing but each column of x will be the data point. Okay, x1 up to xn, and this will be a d cross n matrix. And y is a vector which is diagonal, having entries y1 up to yn, right? And then we have alpha, which is nothing but alpha 1 up to alpha I. Okay. So this is the representation now. Okay. Now we have a condition called the complementary slackness condition. Okay. And it holds when strong duality holds, which means both the objective function and the constraints are convex functions. So when that in that particular case we have strong duality, and in case of strong duality we have complementary slackness condition. Now what does it say? It says that alpha I star, where alpha I star, the star denotes that it is actually the optimal value, okay, times 1 minus W transpose or W star transpose Xi Yi, that should be equal to 0. So either of these two terms should be 0. So we can say if alpha I star is 0, then what can we say? Okay. Nothing much, okay. But if alpha I star is strictly positive, then we can say that W star transpose Xi Yi should be equal to 1, right? That means Xi lies on one of the supporting hyperplanes, right? And this in turn leads to the conclusion that Xi is a support vector, okay, because that is what support vector means, right? It should lie on the supporting hyperplane, okay. So if alpha I star is 0, then we cannot say anything, okay. It may or may not be a support vector, right? So we cannot conclude anything. So the option here is false, okay. Alright, so for this question you need to know what the soft margin formulation is for the SVM, okay. So we know that in soft margin SVM we try to minimize, so minimize with respect to two variables, W as well as zeta, right? And what do we minimize? We minimize norm of W square by 2 plus C times of summation of zeta I, right? I running from 1 to n, okay. So for every data point there is a zeta I, okay. And C is actually figured out using cross validation, okay. That is something which you will see later. And what are the constraints? The constraints are, first of all, we need each of the zeta I to be non-negative, okay. And then we also need W transpose Xi, right, times Yi, okay. So in general we need this to be greater than or equal to 1 in the hard margin formulation, but in soft margin we have that plus zeta I, this should be bigger than or equal to 1, okay. And this should hold for every I, okay, for every data point, okay. That is a constraint. Now observe one thing, see. Alright, so if C is 0, that means that the objective function that we have to minimize, right, that is nothing but norm of W square by 2, right. Now that is same as the hard margin. So that is same as saying that take W to be equal to 0, right, okay. Because when you take W to be equal to 0 and you take zeta I to be, some large value, okay, take zeta I to be some large value. So we can say if C is 0, then zeta I can be as large as possible, right, because there is no cost associated with zeta I, right. So it can be as large as possible. Now what does that mean? That means that W will be as small as possible. W will be as small as possible. Why is it as small as possible? Because see, we have to minimize norm of W square, right. So will be as small as possible. Now what is that W? That is nothing but W equal to the 0 vector, right. It will be in RD, okay. So this is the case when C is 0, right. And if C is infinity, what happens? Like very large C, okay. So this will be nothing but, so if C is infinity, that means zeta i's has to be 0, okay. That means zeta i's has to be 0 for every I, because C is very large, right. Now that would mean that we have a hard margin problem. So this is same as the hard margin formulation, right. Hard margin formulation. Now observe one thing. So now the question says if the soft margin is trained on this data set, okay, the optimal weight vector it returns will be same as that of the one returned by the hard margin SVM, okay. This is not true, okay. Because this actually depends on the hyperparameter C. So this is actually false. In fact, I have generated a random data set, right, having positive and negative points, and you can see that there is one example for there is one case where I have trained a hard margin and another case where I have trained a soft margin, okay. So for hard margin I have taken C to be equal to 10 to the power 10, okay, which is a very high value, okay. And for soft margin I have taken C equal to 1, okay. And these are the lines which we got, okay. Now observe that the W is different, right. So here the W would be something like this, okay. This is W, right, and here the W would be something like this, okay. Observe that these two are different, okay. So this is the W here and this is the W here, so they are different, okay. So that is the whole question, okay. Alright, so in these type of problems you have to remember three important conditions, right. which out of which two of them are the complementary slackness conditions, which say that alpha I times of 1 minus W transpose xi yi minus zeta I is equal to 0, right? And the second condition is that beta I times minus zeta I is equal to 0. And the third condition is that, so this should hold for every data point I, okay? And along with that, we also need alpha I plus beta I is equal to C, right? Now C is given to be 3 here, so I can write alpha I plus beta I is equal to 3, okay? Now let's do it one by one. We need zeta 1, zeta 2 and zeta 3. So zeta 1 corresponds to the first data point, right? So what will be 1 minus W transpose x1 y1? This will be equal to 1 plus 1, which is equal to 2, right? Okay. Now, why is it 1 plus 1 equal to 2? Because see, W transpose x is equal to minus 1, right? Here, this is the line, and this point actually lies on this supporting hyperplane. So we can say this is equal to 2. So we can say alpha 1 times, not alpha I, alpha 1 times 2 minus zeta I is equal to 0, right? Now we have the condition that, and now beta I times minus zeta I, this is also equal to, sorry, I shouldn't write I should write 1, okay? So it has to be beta 1 times minus of zeta 1, this is equal to 0, right? So, and we have the condition that alpha 1 plus beta 1, this should be equal to 3, right? Okay. So if alpha 1 is 0, okay, let's assume alpha 1 is 0, okay? So if alpha 1 is equal to 0, okay, then beta 1 is equal to 3. That means zeta 1 has to be equal to 0, right? Right. That is one criteria. Or if I say that zeta 1 is equal to 2, okay, see, this has to be equal to 0, right? So what does that mean? That means either alpha 1 is 0 or 2 minus zeta 1 is 0, right? So zeta 1 is, if zeta 1 is equal to 2, then we can say that beta 1 has to be 0, right? Because of the second criteria, right? Now if beta 1 is 0, then alpha 1 has to be equal to 3, right? So this is also a possibility, right? But here you observe that we are getting two different values of zeta I, right? So which one is correct, which one is wrong, okay? So to understand that, look at this particular one closely. So what does this say? This says zeta 1 is 0, which means that, see, we have a condition saying that 1 minus W transpose of x1 y1, right, minus zeta 1 should be less than equal to 0, right? This is one of the conditions in the SVM problem, okay? Now if zeta 1 is 0, we can rewrite it as 1 minus W transpose x1 y1 is less than equal to 0. Now what does that mean? That means 1 plus 1, which is 2, is less than equal to 0, which is not true, right? Which means this particular option, right, this particular condition is not true, okay? This is not true. So this is the correct one. So zeta 1 is equal to 2, okay? Now let's do the same thing for the second point, which is x2 by 2. So let's find out zeta 2 and alpha 2, okay? So first of all, observe that it is lying in this particular line which separates the two data points, right? So you can say that W transpose x2 is equal to 0, okay? Because it is lying on the line, okay? Because in fact you can think of it as, perpendicular to the W, right? This is perpendicular to W, right? So W transpose x is 0, x2 is 0, okay? And what will be W transpose x2 by 2? Okay? That will also be 0, okay? Right. So what can you say about 1 minus W transpose x2 by 2? That will be equal to 1, okay? Right. Now and now the condition we have that 1 minus W transpose x2 by 2, right, minus zeta 2 should be less than equal to 0, right? So definitely zeta 2 has to be some. So what will be zeta 2? What can you say about zeta 2? Zeta 2 is bigger than equal to 1, right? This is something which you can say immediately, okay? Now let us go back to the complementary conditions, okay? In the complementary conditions or the complementary slackness condition, since zeta 2 is greater than equal to 1, we can say that beta 2 has to be equal to 0, right? Now if beta 2 is 0, then we can say that alpha 2 is equal to what? Alpha 2 is equal to 3, right? Because alpha 2 plus beta 2 has to be equal to 3, right? So alpha 2 is equal to 3, okay? Okay. Since alpha 2 is equal to 3, right, we need 1 minus, right, W transpose x2 y2, right, minus zeta 2 to be equal to 0 by the complementary slackness condition 1, right? So this is the first and the second condition, okay? Because one of the products should be 0, right? So this has to be 0. That means that zeta 2 is equal to 1, okay? That is the idea, okay? So zeta 2 is equal to 1. Now let us do the same thing for zeta 3, okay? Observe, zeta 3 is very far away. In fact, it's given that it lies on a line which satisfies W transpose x is equal to 4, right? So what we can say that W transpose x3 is equal to 4, right? From there we can say W transpose x3 y3. What will that be equal to? See, y3 is 1, right? Y3 is 1. So this will be equal to 4. So what will be 1 minus W transpose x3 y3? That will be equal to negative 3, right? So what will be 1 minus W transpose x3 y3 minus zeta 3? Okay, this has to be negative, right? This has to be negative. So you can say that minus 3 less than equal to zeta 3, right? But anyway, we need zeta 3 to be positive, right? So that is a condition, right? So this is there, okay? Let's keep it there. Now, what can you say about, right? Now so obviously, since, okay, let me write it. Since zeta 3 has to be bigger than equal to minus 3, or sorry, I think I should write bigger than equal to 0, right? It means that 1 minus W transpose x3 y3 minus zeta 3 is not 0, right? Now that would mean that alpha 3 should be equal to 0, right? But if alpha 3 is 0, we have to say that beta 3 is equal to 3, right? Because the sum of alpha and beta has to be 3, C, right? Now that would mean by the second slackness condition that zeta 3 is equal to 0, right? So that is how we conclude that zeta 3 is equal to 0. Alright, so in the previous question itself, we have found the value of alpha 1 and alpha 3, which are 3 and 0 respectively. So these are already done in the previous question, okay? Now we have to find alpha 4, right? And it says if it cannot be determined exactly, enter minus 1, right? Okay, so let's start with the point x4, y4. So where is the point? This is the point, right? So what is x4? x4 is somewhere on the line W transpose x equal to minus 1. So we can say that W transpose x4 is equal to minus 1 and y4 is given to be equal to minus 1. So we can say that 1 minus W transpose x4 y4 is equal to 1 minus 1, which is equal to 0. Okay? And we have a condition saying that 1 minus W transpose x4 y4 minus zeta 4 is less than equal to 0. Right? Okay. So let me take two different cases. So case 1 is when zeta 4 is equal to 0. Suppose zeta 4 is 0, right? Then what can we say? Then we can say that since, so 1 minus W transpose x4 y4, okay, minus zeta 4, this is equal to 0. So alpha 4 can be anything, right? It can be 0 or it can be anywhere between 0 and 4, okay? Not 0 and 4, it should be 0 and 3. Okay, C is equal to 3. Okay? Since alpha 4 is anywhere between 0 and 3, beta 4 can also be anywhere between 0 and 3, okay? Because see, zeta 4 is 0, so the second slackness is also satisfied, okay? So both the slackness are satisfied, okay? So alpha 4 can be anything, right? Now let me take a different case, case 2, where alpha 4 is some number which is strictly positive, okay? If that is the case, then this particular quantity 1 minus W transpose x4 y4 minus zeta 4, this will be strictly negative, right? But if it is strictly negative, to satisfy the first complementary slackness condition, we need alpha 4 to be equal to 0, right? And since alpha 4 is 0, we need beta 4 to be equal to 3, right? So alpha 4 can be 0 or it can be anywhere between 0 and 3, and it depends on what zeta 4 is, okay? So the answer is that it cannot be determined exactly So it should be minus 1.
Alright, so here we have a graph of 4 type of 0 1 losses. So 0 1 losses are typically used for classification, right? And basically we have to identify which of them corresponds to which. Okay, so again observe that the dotted one, okay, so the dotted line here, this is the actual loss. Okay, so this is the you know 0 1 loss, and we are trying to approximate it with the other convex losses. Okay, so let's start with the orange one, right? So the orange one corresponds to the function which can be written as w transpose x minus y whole square. Okay? And since y is either 0 or 1, you can alternatively write this as w transpose x into y, okay, minus 1 whole square. Okay, so this corresponds to the, so this is nothing, this is known as squared loss. Okay, squared loss. Now let's look at the green one. So the green one can be written as maximum of 0 comma 1 minus w transpose x into y. Okay? So whenever w transpose x into y is less than 1, right? If it is, what happens if it is greater than 1? Then this particular value becomes negative, right? And then this function will take the value 0. See, that is why after 1 it is always 0. Okay, but otherwise it will take the value 1 minus w transpose x. Okay? So this is the function, and this is known as hinge loss. Okay? This is used in SPA. Okay, this is hinge loss. Now let's look at the red one. Okay? The red one is known as the logistic loss, and it's a little complicated function. It's nothing but log of 1 plus e to the power minus w transpose xy. Okay? And this is called the logistic loss. Okay? And the blue one is called as perceptron loss. Okay? It's called as perceptron loss. And what is the function? The function is max of 0 comma w transpose x into y. Okay? This is called perceptron loss. Perceptron loss. Now observe, perceptron loss and hinge loss are almost the same. Okay. Okay, so it should be negative. Okay, negative w transpose x.
Alright, so here we have to find where the logistic loss and the hinge loss intersects. Okay, so what is the logistic loss first of all? So the logistic loss is given by log of 1 plus e to the power minus w transpose x times y. Okay, this is the logistic loss, right? And what is the hinge loss? The hinge loss is given by max of 0 comma 1 minus w transpose xy. Okay, now if you plot it quickly, right, the logistic loss would look something like this. Okay, it will never touch 0. Okay, it can go close to 0, but it will never touch 0. Okay, and the hinge loss will look something like this. So let me denote the hinge loss by a green line. Okay, so let this be 1, and then it will go like this. Okay, so the part of hinge loss which intersects logistic loss is this part. Okay, 1 minus w transpose x. Right? So let's do it. Okay, so at the point of intersection we will have that log of 1 plus e to the power minus w transpose xy is equal to 1 minus w transpose xy. So if I take e to the power on both sides, okay, I'll get 1 plus e to the power minus w transpose xy equal e to the power 1 into e to the power minus w transpose xy, right? So now if I take e to the power minus w transpose xy common, I'll have 1 minus e, right? Or I can write this as e minus 1. Let me write it as e minus 1. E minus 1, that is equal to 1. Right? Or I can write this as e minus 1 is equal to e to the power w transpose xy. Now if I take log on both sides, I'll get log of e minus 1 equals w transpose xy. Right? And this is actually the first option. Alright, so here we have a neural network with the following architecture. Okay, so it has got 5 inputs. Okay, so you can say that the input is a vector of dimension 5, right? So x is a vector in Rd, okay, or 5. Okay, alright, so then we have a hidden layer of size 10 and 10 respectively. Then there is an output layer. Okay, and the question says ignore the biases. Okay, alright, so let me write the input vector x as 5 neurons, okay, because each of them denote x1, x2 and so on up to x5, okay. And then there is a hidden layer and there are 100 of them, okay. I'm not drawing all of them, so there are 100 of them, 100 neurons, okay. Now, so there will be a line from x1 to the first neuron, right? There will be a line from x2 to the first neuron, right? So there will be 5 lines to the first neuron, right? And each line corresponds to a weight. So there are 5 weights. Let me call it W1 up to W5. So there are 5 weights in the first neuron. So in 100 neurons, there will be 50 weights. So I'll write here 50 weights in the first layer, right? Okay. In the second layer, in the second hidden layer, there are again how many neurons? 100 neurons, okay. So again 100 neurons. Now, from the first neuron of the first hidden layer, there will be an arrow to the first neuron of the second hidden layer, right? Similarly, there will be an arrow from the second neuron of the first hidden layer to the first neuron of the second hidden layer. And similarly, there will be 100 arrows, okay, because there are 100 neurons in the first hidden layer. So there will be 100 arrows. So I will write it as, say, W1 prime up to W100 prime, okay. But this is the case of the first neuron. Similarly, there are 100 neurons, right? Sorry, there are 10 neurons, okay. Let me just quickly make that change. There are 10 neurons, okay. So 10 neurons and 10 neurons, okay. So since there are 10 neurons, okay, and also this will be W1 up to W10, right? Because there are 10 neurons, okay. So 10 neurons or 10 weights in the first neuron. So in 10 total neurons, there will be 100 weights. So 100 weights in the second layer, okay. And then we have one output layer or one output neuron, okay. So there will be one line from the first neuron of the second layer to the output layer. There will be one line from the second neuron to the output layer, and similarly there will be one line from the 10th neuron to the output layer, each corresponding to 10 weights, right? So there will be W1, let me denote it by W1 double prime, W2 double prime up to W10 double prime, right? So there are how many of them? This has got 10 weights in the output layer, So how many total weights do we have? 50 plus 100 plus 10, right? Which is equal to 160. Alright, so in this question, let's first see what does binary cross entropy loss mean, okay? So let me denote it by LPCE, okay? Binary cross entropy. So it is given by minus of, so let me write it for a single data point, okay? So there is only one data point. In case of multiple data points, we take an average of all this, okay? But in case of a single data point, we can write this as negative of y times log of, say, p, right, minus 1 minus y times of log of 1 minus p, right? Now, what is y? Y is actually 0 or 1, right? This is the actual or the observed label, okay? And p is the probability, right, that y is equal to 1, okay? And this is actually determined from the model, right? So this helps us with the with the classification, okay? If p is greater than some particular value, we say that, okay, y is equal to 1, okay? But this is also known as the softmax probability, okay? Softmax probability, okay, fine. So it says what is the choice of the activation function. Remember, p, whatever value p takes, right? So p is equal to f of some x, okay? In fact, it is f times something of x, so it's actually, let me write it properly, it's f of g of h of and so on x, okay? So it's actually a composition of functions, right? And the last function acting on it, right, that is the activation function that we are referring to, okay? Now which activation function is appropriate, right? So observe one thing very carefully. So inside log we have p, inside log we also have 1 minus p. So we do not want p to be equal to 0. So we don't want p to be equal to 0 or p to be equal to 1, right? Because inside log you cannot have 0, right? Because then it will be minus infinity, right? Which is not defined, okay? So we don't want these values, right? So the activation function that we choose is the sigmoid activation function. The reason being, the sigmoid activation function is given by 1 plus e to the power minus w transpose xy, right? And this particular value is never equal to 1, is never equal to 0 or 1. It always lies in between 0 and 1. It can be very close to 0, it can be very close to 1. It will never be equal to 0 or 1. But in case of linear and ReLU, at some points it is equal to 0, right? So that is why we have sigmoid function or the sigmoid activation function as the best choice for a binary cross entropy. Alright, so this question is similar to the previous one. In fact, this asks what is the activation function used in the first hidden layer, and this is the output of the first hidden layer, right? Observe that there are 10 real values here, okay? And closely observe that there is a 0 and there is a 1. There are in fact 2 zeros, right? And we just now saw in the previous question that sigmoid function cannot obtain exactly 0 or exactly 1, right? So this is not the sigmoid, therefore it is the first option. Alright, so here we have that for a single data point, right? What is the gradient of the SSE? So what is SSE? Sum of squared errors. So for a single data point it will be nothing but W transpose X minus Y whole square, okay? Now if I take the derivative, it will be equal to, so derivative of this with respect to W, that will be equal to 2 times of W transpose X minus Y multiplied with X, right? Which is same as 2 times of Y hat minus Y times X, right? So it is actually close to the first option, right? The second and third and the fourth options are all false. It is close to the first option, but a 2 is missing, right? Okay, but I think there is some error in the question. It has to be 2 times of Y hat minus Y multiplied with X.